Welcome, everybody, to the PALS seminar. Today's speaker is John Baldwin from the University of Illinois at Chicago, and he will speak to us about infinite combinatorics from finite structures. John?
Yes, okay. Okay, first problem there. Okay, all right. So I'm going to talk basically about how to build various kinds of combinatorial structures, infinite structures, by the method of amalgamation classes, with basically one general method with a lot of variations. And the main point of this talk is to describe how these variations arose and how they can be played with and get in the kinds of things that one could get. And there's one of the applications is pretty much universal algebra. It's appeared in Algebra Universalis, and I'll spend a couple of slides on it. And I had a lot of discussions with people over the last 3 or 4 years about these topics. Right. All right. So I'm going to start in the middle of the 19th century. I'll give a formal definition first. A Steiner system is an element set with k-element blocks, partitioned into k-element, not a partition, but subsets of size k, with the property that each t-element set is contained in exactly one block. Later on, I will talk about things where the t changes and the one will actually be the same in all of this talk. But the generalization is called a block design. So the history, as I said, started in the 19th century. In fact, it turned out that this was published in something called the Ladies and Gentlemen's Diary in the mid-1840s. And a more general question was asked, and then it was relaxed to this one. And Reverend Kirkman proved in 1847 that you can have a Steiner system with three element lines of size n, if and only if n is congruent to 1 or 3 mod 6. What about sufficiency? That took a while. Bose proved it if n was congruent to 6n plus 3, so that's the statistician, and the logician or number theorist Olaf Skolem proved it for 6n plus 1 in 1958. Now, I'm not really going to be talking directly about this finite, this arithmetic conditions, but in fact, an arithmetic condition will turn up as crucially in part of the argument. So a way to think about this in a little more generality is to think of a linear space as being simply a set with a ternary collinearity relation. That means that R holds of a sequence of 3 points in any order and only if they're distinct. And then you say the 2 points determine a line, and you can write this out as an axiom, for shorter axiom about in R. And then connected with this, oh yeah, and I'm going to say this will come up later, but I wanted to get it out here first. Alpha is the isomorphism type of a pair of sets, AB, and then C is some extension of AB that the relation holds. All right, and then a lot of the work on this was done in the 1950s, and at that point, a groupoid was a set with a binary relation. I think now it's called a magma. A quasi-group is a groupoid satisfying left and right cancellation. If you know 2 of the 3 elements, AB equals C, if you know 2 of them, you know the third. And that's the same thing as saying that the group table is a Latin square.
So it's a binary operation.
So yes, the quasi-group is a binary operation. Thank you. That's a very good point. So that's going to come up much later, but the relation is collinearity, but then the groupoid is a binary function. And then a Steiner quasi-group is a particular variety of quasi-groups. the details won't matter to us. And the connection is, if you have a Steiner triple system, every representation of a Steiner, every Steiner triple system is a quasi-group, because R is the graph of such a function. And I'll come back to this later, but what Ganter and Werner proved in 1975 was that every prime power Steiner system admits a compatible quasi-group. But I'm going to construct some strongly minimal prime power Steiner groups that aren't quasi-groups, except in the trivial case where the prime power is 3. And there are strongly minimal Steiner systems that induce. That is, I can add the R and still get a strongly minimal set. And strongly minimal, again, may be unfamiliar, but that's coming up very soon. So what I mean by, what I mean by I may read this a strong or a less than or equal to amalgamation class. So you have a class of finite structures for some fixed vocabulary, which may have functional relation symbols I'll specify, satisfying, well, this strong order is a partial order that refines containment. It satisfies joint embedding, that is, any two structures have a common strong superstructure, and it satisfies amalgamation. Any two extensions of a fixed model have a common. You can close that triangle, that diamond. And now the interesting part is that if you take something, if A is strong in B, then if you take any C in between, A intersect C has to be strong in C. And this I've written in terms of the strong substructure relation, but it's actually it arises from the pre-dimension that I'm going to describe in a little bit. And also you have only countably many structures. Then if you can do that, you can build a homogeneous model, or a generic model, which is the union. It's an increasing chain of these finite models. Every model embeds, every finite structure embeds in it, and it's less than or equal to homogeneous. That means if you have two finite sets, which are both strong and are isomorphic, then that isomorphism extends to an automorphism of the generic model. So the base case of this is the Frise construction that Peter talked about last week, where the language is a finite relational structure, the class is closed under substructure, and less than or equal to is contains. And all of these I'm going to generalize in various ways and more. Yeah, so how does this connect with Steiner systems? Well, a fairly recent paper by Silvio Babina and Enrique Casanovas shows that the class of finite 3 Steiner systems forms actually a Frise class. Here it's kind of a trick. You think of this thing as being a function, but because of this same thing that we noticed before, that 3 Steiner systems automatically were quasi-groups, you have you can just talk about the relational system and get the function. And this class has the amalgamation property and joint embedding, and thus a limit theory T star SQ, Steiner quasi, I suppose. Now I'll say a little more, but the key point for making this work is having the amalgamation property. And this is, well, it's about 50 years old. Every finite partial triple system can be embedded in a finite Steiner triple system. That was proved by Tracer in 1971. I'll mention this now. These Reshofsky constructions I'm going to talk about have a very long history. Not a very long history, it's only 30 years, but a very rich history. And about 15 years ago is my last update of a survey of what was known till then. There's at least as much since. Anybody who would like to play around with filling that out, I'd be happy to talk to them. So what are the properties of this theory of Barbina and Casanova? It has quantifier elimination. I put the definition of type in a little bit later. It's how many descriptions you can have of a point over a set. So there are continuum many types of three tuples over the empty set. The generic model is prime. That means it can be embedded in every model in of this theory, elementarily embedded, and it's locally finite. Every finite subset generates a finite subalgebra. That's in red because we're going to have a variant on this where that's one of the things that fails. And T star SQ has TP2 and NSOP1. Well, what does that mean? Now, here's a diagram, and I'm going to try. We will take about 30 seconds to see if we can do this. Now, if I'm lucky, now I'm on the screen. Yes, and I want to no, not the right one. Oh, sorry, I killed the whole thing. Okay, I'm going to have to just talk about it. Am I back now?
Yes.
Yeah.
Yes.
Okay. Okay. So, unfortunately, this is an interactive website that really is a very nice map of what goes on in first order model theory, and my attempts. I don't know. I've done this before, but today it didn't work. So this theory of Barbina and Casanova is one of these two dots. So the general picture here is that these are Aleph-1 categorical theories, and very, 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 very well-behaved theories. Gets a little bit less, a little bit less, a little bit less, but all of this is the stable class. These are pretty. And then O minimality is here. These are linearly ordered theories that are pretty well defined. And over here you have the independence property, and things get more and more complicated. Here, this is set theory, and this is arithmetic, or vice versa. These are the really complicated theories. And what's called neo-stability is the current fad, and that's why there's all these dots in this area. That's what Gabe and the people of his generation are working on. Okay, and so here we've got this example that is up here. Let's go down a little bit. Now, anyone, if you've looked at these businesses of finding homogeneous universal graphs, the next step is to say, well, let's omit some collection of finite graphs. And so Horsley and Webb, it's also in the last 3 or 4 years, showed that you could have if you have a reasonable collection on a family of finite non-trivial graphs, meaning there is some element in the class which neither extends nor embeds any member of that set, then they actually prove amalgamation and joint embedding and get a countable locally finite generic model. And they have the same kind of notion of homogeneity. It's the model theorist notion of homogeneity. And so they get many different Steiner systems. This was done by combinatorics. They didn't try to put it on the map, and I haven't thought about it, and I don't know if anyone else has or not, but it's probably close to where the Casanova, Barbina Casanova paper. Now, strongly minimal theories. A theory is strongly minimal if every definable set is finite or cofinite. Now, equality. Or if you have the integers under successor, then all you can do with some points is pick out things that are finitely far apart. or vector spaces, or algebraically closed fields are all examples of theories that are strongly minimal. And it's then a theorem that they are categorical, that is, have exactly one model in every uncountable power, and a tower of countably many models. I mean, there's a notion of a basis. Well, I think I'm going to say in the next slide. If you have a strongly minimal set, then if we take the notion to be a notion of algebraic closure in the model theoretic sense, which means A is in the algebraic closure of B, if for some formula phi with parameters in B, phi of AB is true, but phi of XB has only finitely many solutions. So it's the direct generalization from field theory to an arbitrary first-order theory. And if T is strongly minimal, algebraic closure defines a matroid, a combinatorial geometry on the models of the theory. And you have the dimension of the space as a geometry is the same thing as the dimension of the model. And so there's only one in each cardinality. So just to be clear about what I mean by a combinatorial geometry, it's a closure system, that is a set G with a map from subsets to subsets, satisfying that the closure of X is the union of its finite, of the closures of its finite subsets. X is monotone, X is contained in the closure of X, transitive, and it's a pre-geometry, or a matroid, if in addition it satisfies the exchange axiom. So these are the axioms from linear algebra, or van der Waerden a little bit later. And if the singletons are closed, then you call the structure a geometry. And since we're going to be worrying about which notions are definable in general, this is going to be you're going to need infinitely many formulas to find the closure of a set. Went the wrong way. Okay, so now I'm going to talk about constructing them, and why is there an industry of constructing strongly minimal sets? Well, in the mid-'80s, early '80s maybe, Boris Zober conjectured that, well, those examples I gave you before were really pretty much it. That every algebraic closure geometry should either have the lattices of subspaces distributive, and then we call it disintegrated or sometimes trivial. It's like the cases of the copies of the integers under successor. Or they're vector space-like, that's when the lattice of subspaces is modular. Or it's bi-interpretable with an algebraically closed field. Now, in the very late '80s, Grushovsky disproved the conjecture. And what I'm more interested in is not the failure of the conjecture, but providing a method to construct strongly minimal sets that maybe I'll talk about what a flat geometry is, but more to the point, they don't have any associative binary functions. And in particular, the form he phrased it in was that they admitted no infinite definable group. So when I say the method, I mean that the Grushovsky construction actually has 5 parameters. You have to decide on what the vocabulary is going to be. And in Grushovsky, then you take all the finite structures. Although when I say all, I'm thinking of the relations as being hypergraphs. And then some may perhaps universal, but pi 2 will do, axiomatized subclass of these finite structures. And then a function from L0 to the integers. In this case, the kind of generalizations I was talking about before were when you can go into the rationals or even the reals, but that's not part of this talk. That induces a kind of dimension on the definable subsets of the generics. And then using this function, you define a subset, a subclass of the structure. And then still further, in order to get strong minimality, you have a function mu that bounds the number of zero primitive pairs that are bounded by mu. And I will explain that in a moment. And then choose each of these things, and you get a collection of you can have a class U of a certain condition on the U, on the mu, and then you get a whole collection of theories that are very similar. The standard U, capital U, is just saying that mu of C over B must be greater than or equal to, and epsilon became delta of B. So I mentioned primitive extensions in good pairs. So C is a zero primitive extension of A if C is a minimal extension of A such that delta of C over A is zero. So in between, the dimension may go up, pre-dimension may go up, but it comes back down to zero. And it never goes down. C is good over B if B is a real base for this. Like between you have C looks nice with respect to A, but then there's some pieces of B that don't have anything to do with it. So you take the set of those points that are actually connected to something in C, and that's called a good pair. And the good pairs are the things that are going to be that are, if you don't have the mu, there'll be infinitely many copies of a good pair. But the way we make the set strongly minimal is to insist that each one of those sequences is finite. So if I look at a particular model and a particular good pair, I call chi-m of BC the maximal number of disjoint copies of C over B appearing in M. And then K mu is the collection of structures that chi-m of AB is less than or equal to mu of AB for every good pair AB. So once again, I should have CB and A. That, two things got mixed here. But the notation is. I won't try to straighten out the notation, but you have a notion of an extension and you're counting how many extensions there can be. So now how do we, the next issue is to construct strongly minimal linear spaces. Or first, what would happen if you had a strongly minimal linear space? So remember, a linear space is giving you a family of lines of fixed length. But to get a Steiner system, but suppose I just have a linear system, so just a 2 points determine a line. Well, then all the lines have to be finite, because if there's an infinite line and some point off it, then you cross those two lines and you get more points. You draw a line, through the point off and each one of the points on the line, and you get. And then there's more points on that line, so there are infinitely many points that are on the line and infinitely many that are off the line. So then an easy-compactness argument says that if you have a strongly minimal linear system, then all the lines have size at most some finite k. And what will happen in doing this construction is if we set mu of that little triple alpha that I mentioned before, C, A, B, C, C over AB is a good pair. And if we set the mu of that to be Q minus 2, then we get Q lines, because we can add 1 point Q minus 2 times. So we get a line of size Q. So Reshkovsky's basic construction had a single ternary relation R. And for this Steiner system, I still have a single relation. But the class L0 for Reshkovsky was all the finite structures in that vocabulary. Here we restrict to finite linear spaces. And epsilon of A in the Reshofsky case was take the cardinality and subtract the number of realizations of the relation R. Now we're going to do something that comes out of the theory of matroids. This notion is due to Gianluca Paolini. You count lines, and the dimension of a line is the length of the line minus 2. And so now delta of A. So I switched from epsilon to delta to say I've made a specific example here. So delta of A is the cardinality of A minus the number of lines times their length, but minus 2, because every line has to have 2 points. And then you do the same definition of you just say that every subset of a model of L0 must have non-negative dimension. And U is almost like before. Mu of A over B is greater than the value of the dimension of the base, except for one point. If we did that, the 3-point lines would be thrown out, because mu of C over AB would be 1, which is less than delta of AB, which is 2. So we just say for one particular case, we allow that, and otherwise we just make it a Q is whatever. That's arbitrary for our, it's arbitrary for our system, and we allow the Q being 3, which wouldn't have been legal for Reshofsky. All right. And now the theorem that Paolini and I showed is that for every k greater than or equal to 3, there are an uncountable family T mu where the mu satisfies the condition just above, which give you for every infinite kappa, you get 2 kappa K1 Steiner. So they're Steiner systems. And there's no infinite group definable in any of them. All right, so that's one example. The next example I call highly transitive block designs. So, sorry, just make sure I haven't skipped the slide. Yeah, no, the motivation comes from a paper of Evans in 2004. This is David Evans. Trevor Evans shows up later. What David says in his introduction is, for all reasonable finite T, K, and S, we construct a T Aleph 0 K1 design and a group of automorphisms which is transitive on blocks and has S orbits on points. Now, he suppresses the model theory in his paper and published it in the Journal of Combinatorial Design. I'm going to look at it more from the model theoretic perspective, and actually it's it's not his example exactly, although it's certainly the same idea. And that comes from a definition given by Freiberg and Freitag and Musa. Now, in model theory, we have the notion of a stationary type. So a type, again, is a collection of formulas that give a complete description of the relationship between a point or a finite sequence and the domain. And you take a sequence of those points, and any point, and if you take an infinite sequence, independent sequence of those points, any point that depends on the infinite sequence must depend on some n. But the question is, can that n move around arbitrarily within the theory? And I think that the conjecture, I don't know if Jim showed up, Jim or Scott managed to come or not, but whether you can do uniformly a bound that doesn't depend on the theory. But what we give is a theory such that, a theory Tn, such that you will need n points where each time, the first n times, you can be independent and then it can fail and have a non-algebraic extension. And this high transitivity is the crux of making that kind of an argument work. So how do we vary Reshofsky construction for this? We're still going to have a single ternary, instead of a single ternary relation, we're going to have a single R-ary relation. So R is really going to be this probably should have been TRK. Is going, because that's going to be the length of the chain, the NM degree. So you look at all finite structures in that language, but you have an R space, which is, as I previously had for a linear space, except now instead of 2 points determining a line, I'll say R minus 1 points determine a curve. So it's, you know, you're having an analogy to a degree R polynomial. And now for epsilon, or delta in this case, we combine two tricks. One is the Paolini version of counting the line, the dimension of the line or of the curve in this case. There's missing parentheses there. And the other comes from a paper of Holland and myself in the late 90s, where we showed that there was an algebraically closed field with a definable infinite set that was still, well, maybe still had rank 2. And to do that, you split the universe in two parts, where one part of it has the points count 2, and the other part, the points only count 1. And then A is in the language if, once again, epsilon of B is greater than or equal to 0 for all B. And now a trick which appears actually in Reshofsky's first paper, although I had the idea about the same time. To get it to be almost K transitive, you say if you have a sequence of size less than K. Now, in this case, we've only got this one R-ary relation. And so if K is less than or equal to R, that means if you have K points that don't have any connections, then what you do is take any structure bigger than that, which would drive down the dimension, and throw it out. That is, you say that you just add in the universal sentence that structure cannot appear in amongst your finite classes, amongst your finite models. And then what's going to happen is that we get a two-sorted universe. The P part is a strongly minimal theory where and the lines in the universe are infinite, but they each intersect the P part in Q minus R minus 1 points. So that the P part looks like a variant on what I mentioned with Paolini, while in the whole universe, the line is infinite. So the conclusion of this is for every R and K, so that we just have, there is an almost strongly minimal theory, TRK, with two sorts, P and not P, such that for any model of that theory, of some infinite cardinality kappa, you get a tau structure that just specifies the language. It's what's called almost strongly minimal. That is, P is the algebraic closure of P of M along with a finite sequence A bar. And the universe as a whole is a kappa kappa 1 design, an R minus 1 kappa kappa design, but the restriction to the strongly minimal subset P is an R minus 1 kappa K1 design. So there are two orbits on the points, P and not P, and it's transitive the group reacts transitively on the blocks, and in P and in not P, it's transitive on S element sets, or less than or equal to S element sets, for every less than or equal to R element sets. And then the complete type over the empty set has this non-minimality degree that Freytag and Musa were after, along with another notion that's coming up. So this is part of some stuff that we're working out with Freytag and Musa. Okay, now I was inspired by Peter's talk to finally learn something about the small index property. Yes, this says intersection, but it's index, the small index property. And so let's recall here that then Peter kindly loaned me several of his slides, and I'm just, the next two or three are going to be just copied from his talk. Now, here we have M as a countably infinite structure, and G is the automorphism group of M. G is a topological Polish group under the pointwise convergence, that is, basic open sets or cosets of stabilizers of finite tuples. And the crucial point is M has the small index property if every subgroup of index of countable or less than 2 to the L of 0. These turn out to be equivalent, but is open. And then other properties that I'm not going to much deal with, but it has uncountable finality if it's not a countable union. It's Bergman property. Again, we aren't going to actually get into these, so for saving time, I will just go on to the okay. So there's a little subtlety here. So Peter was talking about basically about the countable case. You can make the same notion for uncountable structures. So here I finally wrote down the definition of a type. The type of A over B is the collection P of formulas phi of XB such that phi is true of A and B in some model M. And M realizes P if there's something that satisfies it. M is kappa saturated if every type of it, if every type over any B contained in M with cardinality B less than kappa is realized in M. Now, the reason I bring that up is because there's another paper of Laskar and Shalat in 93 that says for uncountable saturated models, the small index property holds. But in the countable case, there are two possible things to start with. But one is maybe a lot of these examples are L of 0 categorical. Others are L of 0 saturated. But in fact, neither of those conditions is necessary and sufficient. They are L of 0 saturated, but not L of every possible combination of these things is consistent. In particular, the SIP fails for countable saturated models of algebraically closed fields. That's because it's known to fail for the algebraic numbers. I mean, that's a fact that comes up in algebraic number theory. I'm not sure if they call it that, but it's something called Serre's lemma is closely related. And then what Laskar proves is that because of that, it also fails for the countable saturated model. On the other hand, what Zaniar Gardanezad, speak up, Zanya, if you arrived and I'm really killing your name. He's basically proved this result for the infinite rank omega stable Rashofsky construction. I'm going to describe what that means in the next slide, or a couple of slides down. In general, if the theory has the SIP, then the group structure determines the Polish topology. And for countable M, ample generics imply SIP. Exactly how the role of ample generics fits into these new examples of these new theorems of Zaniar, I'm not quite sure. And again, here, this is for omega categorical, which is not my main. So, but I wanted to put up the chart from Peter to point out that what we have is a pure set has SIP. So that's totally categorical, omega stable, just as well behaved as possible. The random graph, do I have? Yes, the random graph is here. Super simple, but it's a long way from there. The dense linear order and Cantor space, that is I think that's the dual space of the atomless Boolean algebra, is up here. And the free group of rank omega, whether that was a complete theory was Tarski's problem from the 30s, I suppose. And Sila and we solved that in the I don't know, what is it, 10 years ago now, but fairly recently, and showed that the free group was actually stable. So what the point is that these SIP structures are just all over this map. It really is pretty much unrelated to any sort of stability classification. So how do you do the construction for SIP versus infinite rank? But for SIP, we're going to look at the theory, which is kind of the easy part of the original Reshevsky thing. You have a finite relational language. You keep the same structures. Now you're going to have, you don't have to just have one ternary relation. You take any finite set of them, and you count the number of realizations of each one of the symbols and add them up, rather than just having one. But this is really just the same thing. And you use the same notion of delta, and you forget about mu. And the result then is that instead of getting an Aleph 1 categorical theory, which will have finite Morley rank, you get a structure of infinite Morley rank. And now what Zaniar has shown, I think, is that the generic, that is the omega saturating model of this structure, has SIP. And that's it's an argument that's similar to what Laskar did, but actually with some quite different ideas using the dimension function. And so if you move on to strongly minimal systems or strongly minimal Steiner systems, whether these results just go over easily or whether one has to do a lot more work is just not quite clear at this point. Again, for the almost strongly minimal structures. So I proved again a long time ago that there was an almost strongly minimal non-de-Zargian projective plane. And this was using the standard methodology and then a little trick at the end. And whether that trick is susceptible to whether it also makes the translation here is, and again, people haven't thought about the highly transitive structures above because we just realized that they were questions to ask about it in the last 2 weeks. And then there are stable Reshevsky structures using an irrational coefficient for the number of relations, and again, what happens with those? I mean, it wouldn't at all astonish me if at least the strictly stable theory was known. But it's a family of questions. Okay, and now I wanted to say a little bit about something about of a more universal algebraic flavor. So I'll say a variety. And now we're doing universal algebra now. A variety is a collection of structures that's defined by a system of equations. And it's binary if all its equations are two variable identities. This is a notion of Evans. Well, now Trevor Evans. And then let's see. Yeah, I don't know exactly who proved these results, but I got them from Ganter and Werner. Given a near field, just say a field for a second, a finite field of well, then it has to be of order p to the n. Define a multiplication by x star y is y plus x minus y times a. Then that algebra is it generates a Steiner quasigroup, a variety of Steiner quasigroups. And now I want to go back to what this Ganter-Werner theorem was. That is, what does it mean to coordinatize a system? And I'm going to call it weakly coordinatized. So a collection of algebras, say a variety, weakly coordinatizes a class of 2K Steiner systems. So 2 points determine a line, and lines have k points. If each algebra in V definably expands to a member of S, that is, if you give me the variety, I will, you give me an algebra in the variety, I will tell you what a line is. Namely, it's each finite two-generated subalgebra, each two-generated subalgebra will be a line. And the universe of each member of the underlying system is the underlying system of some algebra, but perhaps many. I can just plop algebras down on top of it and assign a coordination to it. Now, why can I do that? Because of this two variable identity thing. If you put the quasi-group structure is determined entirely by what happens on individual lines. And so what we're going to do is guarantee that every line has length Q and then put one of these block algebras from our variety on it. So the weak coordination of, I don't remember who ST and Evans. Well, this is the remark that if you have a variety of binary idempotent algebras and each block of a Steiner system admits an algebra, so does S. And then Ganter and Werner show for each Q, the class of Q Steiner systems is weakly coordinatized by a 2Q variety V of block algebras. Now the question is, can this structure actually be defined in the Steiner system? So I built a minute ago a strongly minimal Steiner system. Does it know that this group structure is there? And the answer is no. In fact, there are no definable binary functions on this system with one modest additional hypothesis. Let T mu be a strongly minimal theory as in Reshkovsky's construction or as in my construction of Paolini. Let I be a finite set of independent points. Then, no, but yeah, I need this. What I call it the DCL star of X are the things that are in the definable closure of X. That is, there is a definable function of the elements of X that gives you A is in the star closure if there's some function of the X elements in the language that gives you A. But it has to use all of them. it's not in the definable closure of any smaller set. And now, if we have a certain technical condition that mu has the property that mu of A over B is always greater than or equal to 3. You never get less than 3 copies of any zero primitive extension. Then the DCL star of this I is empty. And so every definable function is essentially unary. That is, there's no function that can really depend on 2 variables. And if you want to get rid of this hypothesis, you strengthen this notion to say, I don't want just the definable closure, the star definable closure to be empty. I want the symmetric definable closure. That is, you take not things that are fixed under permutations that fix I pointwise, but rather by permutations that fix I setwise. Then there are no empty set definable symmetric, that is, functions that do not depend on the end of the argument, truly binary functions. And that's enough to get that the theory does not admit elimination of imaginaries, which we haven't discussed. And it remains the case the algebraic geometry, closure geometry is not disintegrated. So this is a very complicated argument. It's about 30 pages to prove this theorem just for the Reshofsky case. But it yeah, I'm just going. Yeah, okay. So I think I've gone quickly through a family of examples. If anyone has questions, I'd be happy to continue. I'd like to thank Peter both for the invitation and for his help with providing this, and also Zanya, who gave me some of the slides, and we had many discussions over the last week. Thank you.